All right, looks like we had 3 to go. So here it comes, number 3. The problem was we're looking at the sum n equals 2 to infinity. This was the one with 1 over n natural log of n. So we're going to look at the integral that goes along with this, integral from 2 to infinity of 1 over x, natural log of x, dx. And in order to do this integral, it is going to be a u substitution. And the more complicated piece here is the natural log of x. So we pick that off and call that u. Then our du is 1 over x dx. And that's exactly what we have left here. Here's our dx numerator, 1 over x, and that's all of du. So if we rewrite this now, we get integral, well, it's going to change, but I'll leave that open. And it's 1 over u. That u is the natural log of x, and then the 1 over x dx, all of that is du. So we're left with du over u. We know what that is. That's natural log of u, absolute value, and u was the natural log. So we end up with the natural log of the natural log of x. We're going to evaluate this. We're going to evaluate this from 2 to infinity. Okay. That's all of your reminds coming through all at once here, which is good. The brain break. Anyhow, natural log of x, we're going from 2 to infinity. We substitute those in. We get the natural log of infinity, and I am shortcutting it here without the limits, just plugging in the infinity. Hopefully we get that, minus the natural log of 2. Well, a natural log of infinity is approaching infinity, so the whole thing is there's no answer. This is a DNE. This diverges. Therefore, the summation diverges. That's number 3. Let's take a look at number 4. Number 4, this was sum n equals 1 to infinity of n over 1 plus n squared, switching to the integral 1 to infinity x over 1 plus x squared dx. This is pretty much a u substitution. We don't have to do it. The u would be 1 plus x squared. And then du would be 2x. So we just need to have a 2 here. And now I've got the perfect du. Of course, we need the half. That gets us an integral of 1/2 natural log of 1 plus x squared. We're going to evaluate from 1 to infinity. I don't need absolute values because 1 plus x squared is always positive. Anyway, once we substitute my infinity in as my first step in the evaluation, we get 1/2 natural log of 1 plus an infinity squared. We're done here, minus whatever, because this is off to infinity. This diverges. Therefore, the sum diverges. 1 to go. Number 5. And number 5 was sum n equals 1 to infinity e to the n over 1 plus e to the 2n. So we're going to go ahead and try this with the integral test. Integral 1 to infinity e to the x 1 plus e to the 2x dx. And if you look at this enough, and it may not have been obvious to start, we know that e to the 2x is also e to the x quantity squared. If u then is e to the x, this becomes 1 plus u squared, and e to the x dx is our du. So what we're looking at here is a du over 1 plus u squared. We know what that is. That's an inverse tangent. So what we end up with up here is an inverse tangent of our u, which is e to the x, and evaluate from 1 to infinity. When I substitute in the infinity, we get inverse tangent of e to the infinity, it's a big number, minus inverse tangent of e to the 1. E to the infinity is just infinity. What angle, the question becomes, What angle has a tangent of infinity? Well, look way back over here, because we know our tangent graph heads toward infinity at pi over 2. So the angle, pi over 2. So this is pi over 2, and this is just inverse tangent of E, whatever that is. But that's a number. That's a convergent value, and we don't care what the value is. We just care that it exists. Therefore, the sum converges for this last problem. And that's it. Now, as I was saying before, integral test is not on the revised AP exam this year. However, the next two topics that we're going to get to starting, I guess I'll post them probably Monday, late Monday, involve the integral test as a way to prove the two tests that we're about to look at. So coming up next, we'll need this idea, and that's why I thought it was a good idea to take a look at it. That's it. Those of you keeping up, again, thank you and keep going.